Welcome back to Codex. Our speaker today is Doug Cochran from Arizona State. Professor Cochran is an expert in frame theory, waveform design, and signal processing. Today he'll tell us about generalized coherence tests. Take it away, Doug.
Good. Thank you very much, Dustin, and thank you guys for asking me to give this talk. I have to give. I've spent the whole time talking to people before the room filled up with disclaimers about how I'm not that happy with the way the talk came out. But I'll tell you, it's kind of a difficult thing to put forward, put together for me, because it's motivated by statistical problems. And I know that this audience, there are people in the audience who have a lot of statistical expertise, but this is in general not a statistics seminar, and many people in the audience are not so much statistical people. So part of it is going to be should be easy to go out and get some other piece of your lunch. If you're familiar with some of the easy statistical stuff that I'm going to go through. But I will eventually get to a little bit of geometry. I'm going to do some of the mechanics in fairly explicit detail, and then by the end, in the interest of time, there's more to the story, but I'm just going to synopsize it. So one thing that will only come up at the end is what's a generalized coherence test. But let's go. Oh, by the way, this is joint work with my longtime colleagues and collaborators, Steve Howard and Songsi Skiri and Nongkai Boon from Australia. Part one. So I want to introduce to you, and particularly for those of you who don't do a lot of statistical things, this a specific example of a binary hypothesis testing problem. This example has many of the ingredients, although it's very simple itself, it has many of the ingredients of more complicated problems, including the one that I will focus on most of the talk. It's intended to be kind of a launching pad to appreciate what we're trying to do in the body of the talk. So consider two hypotheses, and this is fairly standard for this kind of problem. The data X is realized from some distribution under hypothesis 0, I'll call the null hypothesis, and under the alternative hypothesis, denoted H1, it's realized from a different distribution. So I've not been careful here about trying to use notation that indicates when I'm talking about the random variable or random vector X and a realization of it. I think it should be clear through most of it. And in this problem, under both hypotheses, X is Gaussian, real Gaussian, in vector. With under hypothesis 0, it has mean 0 and covariance matrix, the identity. So it's called white Gaussian with 0 mean. And under hypothesis 1, it's also white Gaussian, identity covariance matrix with mean vector mu, which is just the one vector all ones. So there's an important result in hypothesis testing called the Neyman-Pearson lemma, which tells you that the optimal decision rule, and I'll say what I mean by optimal in just a minute, has the form that the test should decide in favor of hypothesis 1, looks at the data, it should decide in favor of H1 if this ratio exceeds a threshold. So this ratio is you take the realized datum, here X, put it into the form of the probability density conditioned on H1, and do the same thing for the probability condition on H0. These are both values of probability density, so they're non-negative numbers. You take this ratio in general will be a positive number, and you compare that to a threshold. If it exceeds the threshold, you decide in favor of H1. If it doesn't exceed the threshold, you decide in favor of H0. So throughout this we have this arrow H1, which is different than H1. It denotes the decision of the test in favor of H1, and the other thing can decide is in favor of H0. We have X is the observed datum, the realization of the random vector X, and this, I said this decision rule was optimal, and I haven't told you what this tau is. Well, it's optimal for any choice of tau in the following sense, that if once you plug in a tau, there is going to be associated with this decision rule a probability that you decide in favor of H1 when H0 is actually true. So type 1 error in statistics, and detection theory call it false alarm. So I'm going to fix this, and this rule is optimal in the sense that given that I've fixed a value for the probability of false alarm, it gives me the maximal probability of correct decision. Okay, good. This ratio here is usually called the likelihood ratio, and it's if you know explicitly the probability densities of the data under both hypotheses, that's just called a simple test, you can apply this and get a decision rule that is optimal in this Neyman-Pearson sense. So why aren't we done? I mean, the answer is that most of the time you don't know these probability densities as explicitly. They will depend on some unknown parameters. So people use all sorts of tricks to it's called compound tests. So in a compound situation, people use all sorts of tricks to deal with the unknown parameters. Treat them as random variables for which you know the distribution. From the Bayesian style approach, you integrate them out and marginalize. You can estimate them. This is a generalized likelihood test if you use maximum likelihood estimation. So it's a can of worms once you get away from the simple test. And sometimes the problem of, well, most of the time, the problem of finding a decision statistic, and I'll talk about that term more in a minute, that has any sort of desirable properties in terms of optimality is a challenging problem. So in this simple example, this function, the likelihood ratio, denoted by lambda here, is a decision statistic, happens from Neyman-Pearson limit to be optimal in the sense I described. It's a number, right? So it takes the data, which is a realization of this random n vector. So it's a vector in Rn, and it maps it to the reals. And the test, well, what can happen? It either the likelihood ratio exceeds the threshold or it doesn't. So it divides the data space, it partitions it into two pieces, a region in which if you get a datum from that region, it decides H0, and then the rest of it decides H1. In this case, it turns out that it's you can calculate, because the form of these Gaussian density functions is known explicitly. You can actually calculate this. Actually, there's minus signs missing here, but they cancel out. And it turns out that comparing lambda of x to a threshold is equivalent to comparing this other scalar statistic rho of x, which is just the dot product between x and this is supposed to be the mean mu, the known mean mu to a threshold. So you take the data, the measured datum, you project it onto the subspace, into the subspace of the vector that the known mean. If that number is big, you decide in favor of H1. If it's perpendicular to that or even pointed the other direction, then you decide in favor of H0. So this is a fairly standard thing. Getting there's not a detection statistic that is even named and Pearson optimal. There are maybe many equivalent decision statistics for this problem. This particular simple problem has a sort of stupid invariance, but it serves for me to describe in part 2 what I mean by invariance of the problem. So if you think of the permutation group acting on the data space X by just permuting the order of the components of the vector. So that doesn't change anything, right? I mean, that in under H0, well, the mean stays 0. This is a linear function, and the covariance matrix is, well, it was the identity to start with, so now it ends up with a P transpose. P is a real unitary orthogonal. So this ends up having exactly the same form. And under H1, it doesn't change anything either. So the entire problem, both hypotheses, you say that the hypothesis testing problem is invariant under this action of the permutation group. It's not a very interesting invariance, but it's what we mean by the problem being invariant. You have a group, it acts on the data space. The distribution of the observations stay the same, or the hypotheses stay the same, or under the action of that group. And it should be no surprise that the statistic, we'll just take the simplified one, rho, is also invariant, right? So if there's a symmetry in the problem given by an invariance to a group action that, and you have a decision statistic that's somehow not invariant to that same group action, it's not good. You want the decision statistic to reflect the invariances of the problem. In this case, the orbit of a datum, in vector under this action is just consists of all the in factorial, I guess in principle, points in Rn that come from swapping around the components of vector. So it's there's an invariant. You can identify the invariance with this with the invariance of this problem with this sort of geometrical object, the set of points in a space. So that's it for the preamble. I think that this would be the part in the restaurant where the couple are planning whether to hold it up or something like that. That's the first episode, the first chapter. Dustin was able to quote from the movie earlier, but that's true. Okay, so we're now on to part 2, which I believe is where Samuel L. Jackson and Benny Barbarino, whatever the guy's name is, are calling on the the people who have scammed their boss. So I'm going to tell you about a more complicated statistical hypothesis testing problem for which the standard set of solutions are known as generalized coherence tests. Now, this is something that I worked on many years ago. It turns out to be, these coherence tests are determinants, or at least functions of the eigenspectrum of some grand matrix formed from the collected data vectors. So without going into detail about what these turn out to be, I'm going to talk about some invariances of the problem. So let me tell you the problem first. There are M sets. Each set has K vectors in it, and these will be complex vectors now, in complex n space. And we assume n is larger than K. It's usually much larger. So there is, there's basically no way that this set of vectors spans the full space, see it. And we're going to assume that these vectors are zero mean, complex, normal, and they're also white. Within each vector, the components are independently distributed. I don't think that that's so important to the problem, but it's just a more or less a disclaimer about the setup. So you can take for each M, for each set, you can form an n by k data matrix, which I'll denote by x sub m, which has the vectors in that set as its columns. And we're going to assume that the set of vectors, I've already said something about the individual vectors, we've assumed that the set of vectors are jointly normal and with zero mean, and covariance, for the mth set, the covariance will be R sub m. So in particular, the mth vector, given the covariance matrix R at M, has this sort of Gaussian distribution. Right. So what we would like to do is to realize M of these vectors, and test the hypothesis that the M sets of vectors are mutually independent. Now, we're not talking about the vectors within the set. They're correlated according to this matrix R sub m. So within the mth set, the k vectors that live there can be all correlated with each other in whatever way. But the question is, from set to set, are they independent? So let me digress, as though I haven't enough already. Probably even those of you who haven't done statistics since you were an undergraduate know that being uncorrelated is not strong enough to imply independence. Independent random variables are uncorrelated, but being uncorrelated doesn't tell you that random variables are independent, except in a few special cases. Probably the most important one is if the random variables are jointly normal, then being uncorrelated implies independence. So the independence in the case of joint normality is equivalent to the covariance matrix of the random variables or random vectors being diagonal. So we're going to assume for each M that the data matrix has full rank. Now, that sounds like maybe it's a strong assumption, but it's not really, because under the assumed distribution that was on the previous slide, that it will be full rank with probability 1. So there's by doing this, we're ignoring a set of measure of probability 0. And the set of such matrices, is actually this should be X sub m, is yeah, a complex Stiefel manifold, non-compact, right? So it's an open subset of complex in k dimensional space, and its complement, as I mentioned just a minute ago, which consists of all the non-full rank matrices, has probability 0 under the assumed distribution. So the hypotheses come out looking like this. I already sort of hinted at this. Under the assumption of independence, there will be some kind of a structure on the covariance matrix, and under the null hypothesis, the covariance matrix is just a non-negative and just positive definite matrix. So let me be specific about what the structure is. So I'm going to note by this fancy P sub L for given L, all L by L positive definite Hermitian matrices. These are the kinds of things that are covariance matrices. For P sub L to the M will be block matrices with L by L blocks. So it will have M L by L blocks on the main diagonal and the rest 0. So this thing with a superscript M is telling you block diagonal. And let's just give the distribution again. Under H0, we expect that R should have, okay, it should be positive definite Hermitian with size mk by mk. Anything will do. Under H1, if the independence hypothesis, R should be diagonal. Well, not diagonal. Remember, there are k things in each of the independent components, so it should be block diagonal, with the blocks being positive definite Hermitian matrices. So those are the two hypotheses. So actually this would, I mean, yeah, so Emily's yawning a bit, probably had a hard night. So let me raise a quiz question that will maybe get her thinking about this a little bit with no statistics. What can I do to X that won't change this problem?
Permute the blocks.
Very good. So that's certainly something I could do, and I could. So Dustin's answer, in case you didn't hear, I could apply an action of, well, essentially the permutation group tensored with the identity, which just switches the blocks or the positions of the blocks around. So that doesn't change. It doesn't affect either hypothesis. Any others that come to mind? Well, there's only, I mean, the obvious one, right? I mean, I could multiply X by a block diagonal matrix. So that's going to, well, it's certainly not going to change this, but it won't change this either. The block diagonal structure of the matrix that I'm multiplying the data by is going to be reflected again in this parameter matrix R. So those are the invariances that we're going to be talking about. I've already spoken some. This slide was done before some of the earlier ones, so I've already told you about the decisions. What the datum is, it's a realization of some random matrix that we have described to the distribution of. So look, the entire general linear group, these data matrices is in my MK acts on this through, or it's a by right multiplication. I'm sure I got the dimensions completely right. Does n by MK can act on it? Yeah, I think that's right. So yeah, there's this action, which was not one of the ones that anyone gave in the answer to the quiz. And the reason is that it preserves H0 just fine, but it screws up H1. So it's not an invariant, that the entire problem is not invariant to that action. So I should note that if you multiply under this action, the parameter R gets there's a corresponding action on the parameter R, which is just like conjugation by S. So good, this just repeats what the hypotheses are. H0 is unaffected by, as I said just a minute ago, by the action of GL, of the entire GL. But H1 is affected. So subgroups of the entire general linear group MK, under which the action of which both, I told you I made them up weekend, are unaffected, are the two that we just spoke of. There's a subgroup comprised of block diagonal matrices, which, remember, the superscript tells you that it's block diagonal with the blocks having this structure. So block diagonal matrices with K by K invertible blocks. And that, just simple calculation, it preserves both hypotheses. And there's also this one that which is actually I think the less obvious one, but the one that Dustin came up with immediately was you can permute the blocks. So there are two subgroups of the general linear group that preserve these symmetries under the action that we described. So I'm going to define a subgroup of the general linear group by what amounts to, well, by generated under composition by these two subgroups. This GLK subgroup, the first one, is a normal subgroup because you could just check whether the conjugacy condition is satisfied. And F can be seen then as just a semi-direct product of these two subgroups. So F itself is a subgroup of this GL and K, and it's comprised by semi-direct product of these two other subgroups. And there's actually another symmetry that we didn't mention. It turns out it doesn't really play into the application. You could actually do the same thing that we did in the simple example and just take the entire, each of the vectors and permute its elements around. Yeah, I don't think you really get an invariance, but you get sort of an equivariance out of that. But it turns out in any case that it's not important to the goal which we have in mind for the exploitation of these invariants. So Yeah, we're going to try to obtain explicit characterizations and geometrical characterizations of these invariants by decomposition of this invariance group F into a hierarchy of subgroups. So start with the S part. So if you have a matrix in GLK, then you can write that uniquely as the product of a unitary matrix, K by K, and an upper triangular matrix with real and positive diagonal elements. So a representative yeah, so in particular, the GLK component of this F has a subgroup that it consists of these upper triangular matrices just described. Well, of block diagonal matrices that are comprised of these upper triangular matrices as just described. So yeah, why do we care? Let's look at at what happens under the action of the subgroup. So you take one of the data matrices, and recall that it has full rank by assumption. So there's a unique decomposition of that data matrix XM in this form as the product of a orthogonal matrix, or a matrix with orthonormal columns and one of these upper triangular matrices. So right, I mean, this XM is not square, but it's inner product. Grassmannian is identity. So that each orbit under the action of TK, I mean, has this representative, which is an orthonormal K frame. So this matrix XM twiddle, which has orthonormal columns, it has K orthonormal columns, represents an orthonormal K frame in Cn, and such so that each orbit has one of these orthonormal K frames as a representative, and of course that's a point on the complex steeple manifold. So the invariant of X under this action by the subgroup, this T subgroup, is they're identified with points on the complex steeple manifold. And remember, this is only on one set at a time. If you're looking at the whole thing, extending to the action of TK to the M, so you have now a full thing consisting of these TK blocks acting on the full on the full X. The maximum variants are ordered sets of M ordered points on the steeple. So okay, well, that's not really more satisfying than this thing of in the simple problem of, well, we had a bunch of points and that were the invariants, were the orbits of that represented the orbits under the action. So let's move to a little bigger group under so the actions of these individual TKs were the invariants are represented by points on a steeple manifold, Yeah, that thinking about it kind of hints at what probably the invariants are for this each of the bigger groups, GLK. There's how are steeple manifolds and Grassmannians related? For each subspace, you have many different orthonormal bases. So if you think of, there's a fibration where the stalks consist of a shitload of orthonormal bases over each point in the Grassmannian, right? So there's you might expect that somehow that we've seen what the invariance of this subgroup of GLK look like. Let's see, it's smaller, so it should probably have more invariants. This is bigger, should have fewer. So it's essentially, we'll see explicitly in a second that it's a squeezing down the invariance from points on Stiefel manifold to points on Grassmannian. So it's going to choose, you essentially can choose one you get the invariants become the subspace represented by by each of the choices of orthonormal bases in the previous in the smaller group action. So let's start out with one of the data matrices, and look at the span of its columns. It's just full right by assumption, remember. So its columns are going to span a k-dimensional subspace of Cn. The action by a matrix S in GLK takes F, does this, takes X to Xn times S. Well, yeah, GLK, so this is an invertible operation. So the span of the columns remains exactly the same. The respective, so the columns of XM and X twiddle M span exactly the same subspace. And there will be, in fact, I don't know how much this really matters, a unique X such that, yeah, so this isn't, it's just saying what I said before about its invertible action, right? There's a unique X such that this thing with orthonormal columns has this form. So it's what I'll hand wave further, and to build on my previous hand waving, this is just a way of picking a particular orthonormal basis for each subspace defined by the columns of some X. So every element in the orbit, in this orbit, XS with S GLK matrix, corresponds to the same k-dimensional subspace, and distinct elements of the orbit correspond to distinct k-dimensional subspaces. So in other words, the orbits of the action of GLK on XM, this one component of the data space, are indexed by the complex Grassmannian, and then when we go to the full data space, you have associated with that as a set, an ordered set. For each of the blocks, you have an ordered set of points. For each of the blocks, you have the invariant is a point on the Grassmannian, And for the full block matrix, it's an ordered set of M points. Now, there's still this piece S, which remember was the permutation of the blocks. We haven't accounted for this. If you action by something in the full in this group F, which was the semi-direct product of GLK, which we just looked at carefully. This is the thing that we've defined. We've identified invariants with ordered sets of points in Grassmannian. We have to account for this remaining piece, which was, remember, the one that scrambled the blocks, permuted the blocks. Yeah, but as you would expect, that with yeah, each element of the data space has essentially consists of a vector of these smaller x's, each which has a Grassmannian point as representing the invariance under the action of GLK, but this S permutes these around. So whereas for this component of F, we have ordered sets of points on Grassmannian representing the invariance. Once we factor in these, that we don't care about permutations, then it takes the ordering away. So the maximal invariant statistic, and I haven't really described much what it means to be maximal. I think I had that on a slide. I should go back and say, is a function of the maximum invariant decision statistic under the action of this group of invariances. F is of the problem is a function of these of M unordered points on the complex Grassmannian of K spaces and in space. And let me go back here. I don't think what I talked to variances. Yeah, this I sort of skipped over. There's an invariant test statistic under the action of some group is a maximal invariant statistic if you have the value of the statistic on two different data vectors, two different data is the same. It implies that one of the data is in the orbit under the action of the group of the other one. So essentially, the maximal invariants are associated with distinct orbits under the action. So let me move, having dragged you through this mechanics to conclude. What time is it anyway?
10 till.
5 minutes left.
Oh, okay. Yeah, good. So let me drag you through a little bit of this is, what do I call this, the epilogue? The epilogue is kind of the why. So in the first example, the simple example, the name and Pearson limit suffices. It tells you what an optimal test statistic or decision statistic is, because the hypothesis structure is very simple. And of course, that statistic does turn out to embody the permutation invariance of that particular testing problem. In more complicated problems, such as the one that we've been talking about, there's typically no shortcut to get a decision statistic. So instead, it becomes sort of a design problem. And well, I want a statistic that's good. Like some men hunt for something, others hunt for food. All I'm hunting for is an outfit that looks good. So you want a test statistic that's good in some sense. The sense, well, one sense that it should be good is that it should embody, that it should encompass the invariances of the underlying problem. So one seeks to look for, remember, these test statistics are just functions from the data space to usually the reals. You're looking for functions that embody the invariances in the sense that if you think of the invariances as orbits of individual data under the action of the group of invariances, you want to have the test statistic that function should be a function that is constant on each of those orbits. And Dustin talked about this the other day in a different seminar, not starting from a statistical point of view, just in invariant functions. So the design procedure is you try to sort out what the invariances of the problem are and the associated group action. Look for a maximal invariant statistic, essentially look for what the decomposition of the data space into orbits under these actions of the invariance group, and then proceed to do statistical analysis on these things. Well, in our case, we've gone to some, I wouldn't say to pain, but I've made it a point to describe these orbits as geometrical things, right? Points in some space. And it turns out that for this independence testing problem, that we end up with subsets of some very nice space, this Grassmannian, which has some properties you don't necessarily see everywhere. One is it's a compact manifold. It's not a Lie group, but it still has it's a quotient of Lie group, so it has a Haar measure of an invariant measure, and the associated volume form is well understood. So with a volume form, you can define probability densities naturally as Radon-Nikodym derivatives of a probability measure with respect to this invariant measure. And another thing which I think now we're in the domain where everybody here knows this. I mean, the Grassmannian is covered by one chart. So, you start taking differential geometry, well, you need to have an atlas of charts and you need to have compatibility and blah, blah, blah. Here, one chart will work. It covers the whole thing. Oh, except for a set that is of measure 0 in this volume, in this Haar measure. So yeah, for integration, that's not going to matter. So you can take integrals on the Grassmannian. When you write them out, they're just integrals over a region in Cn or R2n. So you could do them by ordinary calculus. It's sort of like spherical coordinates in calculus, right? You're not worried about what the two forms look like on the sphere. I mean, you just tell the kids that, well, you take the regular integral except you throw in some factor, which is in fact that form, and you can do the whole thing from 0 to pi and 0 to pi over 2 or something like that. So the Grassmannian has this nice property for doing calculations as well. We've shown how to organize and work that that continues from this, how to organize these collections of subspaces that comprise the maximal invariance by assigning orthonormal basis to each subspace in a smooth way, right? So this means that if you want to integrate a test statistic, well, you grab a point from each of the orbits. Well, if you can align these, if you can align these orbits in such a way that you can integrate over this set that's associated with you can associate a bunch of these point sets into a nice region that you can parameterize using this coordinatization of the Grassmannian and do calculation on it. You can do this last step, doing probabilistic likelihood, do probability on the orbits, on the maximal invariance. So why do you want them to be geometrical, in particular be points in some space where you know how to do calculus? Well, because you can do calculus on them, and that's as I think everyone remembers from their undergraduate probability class, that doing probability is a lot about being able to do calculus. So that's it. I know that this was I have my own issues with the organization and the flow of this talk, and perhaps it would have been better if I had just started with the middle part and continued further into showing how to do this pasting of these point sets together into nice regions where we could do probability calculations. But yeah, we'll save that up for later. Maybe actually we'll begin on the next topic. So that's all I came prepared to say.
Awesome. Well, let's thank Doug by smashing that reaction button.